Good morning to everyone. So in the previous classes, we just started analog to digital converters and digital to analog converters. So this is a new concept we just started, just we newly started, and we discussed about the introductory concepts, and we have seen the general basic block diagram for digital to analog conversion, and we have seen the first classification of weighted resistor type digital to analog converter. Okay, so in the concept of this conversion, analog to digital conversion or digital to analog conversion, we are at the discussion of digital to analog conversion. Two types of configurations we will discuss in these converters. One is analog to digital, and second thing is digital to analog. Now we are discussing about digital to analog. So there are various types of classifications and configurations involved in digital to analog conversion and analog to digital conversions. So what we discussed in the previous class means, so in the basic introductory, in the with respect to the concept of data converters. So what is meant by a data converter means? So mostly we discussed about the concept of physical quantities, electrical physical quantities like voltage, current, temperature. Okay. So that means here there is an application, typical application in which analog to digital conversion and digital to analog conversion happens mostly. So here we have analyzed a concept that is called data converters. Here the concept is nothing but data converters or data conversion. That means here converting the signal of analog to digital and digital to analog. So by using what are the parameters we can use while converting this analog to digital and digital to analog means. So with respect to the parameter specifications, we use the electrical physical quantities. So what are electrical physical quantities? Voltage, current, power, wattage. So these are all nothing but there are various electrical physical quantities. So these are specific. So we use these type of physical quantities help, and we can do this type of data conversion. Okay, so mostly if we see the signal performance in our electrical perspective, every signal exists in analog form in nature mostly. So why we are doing this type of conversion means in order to provide an accuracy, precision, okay, and representation of signal in a proper manner, storing of signal in a proper manner, transmitting the signal, processing the signal. So while you seeing all these considerations into various constraints, we have used the concept of conversion, data conversion, or data converters do data conversion mostly. So how can we do this type of data conversion means, so what is the main purpose of doing this data conversion means we have to transmit the signal or we have to process the signal mostly. So in order to transmit the signal and to process the signal, the noise of the signal has to be eliminated, because if there is a noise in the signal, it can be transmitted or it can't be processed properly. So in order to eliminate the noise free features, in order to improve the performance of the signal, we are using this type of conversion techniques. So what is the purpose of conversion? Means here, in order to, we already discussed the transmission of signal or processing of the signal, we need to convert the pulse, say analog signal into digital pulse or digital pulse into analog pulse. So this improves the efficiency perspective. Efficiency perspective of the signal is improved with respect to these parameters. And also in the previous class, we analyzed the block diagram. We analyzed the block diagram of analog to digital conversions and digital to analog conversion. So at this constraint of analog to digital conversion or digital to analog conversion, what we stated means, so we analyzed the block diagram in the manner of a cascaded approach. It looks like a closed loop cascaded approach. You know, most of you are very familiar with the term cascaded approach. Cascaded in the sense, so the output of first stage is connected as an input to the second stage. Okay, and output of the second stage is connected as input of the third stage. So up to nth stage, this is going to happen. Up to nth stage, this is going to happen. We can't say it is an infinite loop. Okay, it is a finite loop. That may be a closed loop condition or it may be an open loop condition. So here in the concept of analog to digital conversions and digital to analog conversion, we have used the same schematic of a cascaded approach. That means one stage output is connected as input to another stage. Another stage output is connected as input to the other stage. That means this is a continuous process or a continuous approach. So what we have did means here, look at the block diagram. Just we connected the plant. We plant in with respect to there is a plant. From the plant we have just taken an analog signal with the help of a sensor. Okay, that means here the sensor will sense the analog signal and that is processed as an output, and that output of analog signal is fed as an input with respect to the anchulizing filter. Okay, anchulizing filter. So this anchulizing filter is nothing but mostly the low pass filters which we are talking about, anchulizing filters. And next, that anchulizing filter or low pass filter will act like a band limit filter, not band stop filter or band reject filter, not like band stop filter or band reject filter. It is a band limit filter. It will limit the unwanted frequencies and it will eliminate the noises. And next, the analog signal, smoothened or processed analog signal is forwarded to the sample and hold circuit. Look at here. Next, forwarded to sample and hold circuit. So what does the sample and hold circuit do? Sample and hold circuit will improve the performance of this analog signal. Okay, so it will convert that analog signal into a discrete pulse. Okay, there is a difference between analog pulse and discrete pulse. Okay, and that analog pulse is converted into discrete pulse with the help of sample and hold circuit. Okay, and next that and discrete pulse is fed with respect to ADC converter. ADC converter in the sense analog to digital converter, where the process of data conversion is done. So simply from the resistor we can't, simply by taking the signal from the sensor, we can't connect that to analog to digital converter. Most of the people just posted the queries in the yesterday's class, and some of the people even DM to my WhatsApp. Why can't we just use a sensor and next forward that signal to ADC? Why this so much cascaded connection? That makes the circuit quite fuzzy and that makes the circuit quite complex. Most of the people ask the question. So here what's happened means the smoothing of signal and conversion of analog signal into discrete signal is important. Why means without uh, band limit filter or anchulizing filter, there used to be unwanted frequencies will enter into the converter and the converter circuit will get damages. And second thing is directly we can't convert the analog signal into discrete digital pulse. First we have to convert this analog pulse into a discrete pulse. Okay, discrete pulse is not digital pulse. Most of the people is having this type of misconception. Most of the people saying that we have studied the sample and hold circuits, so analog pulse is converted into discrete pulse, right? That means it is somewhat digital. No, discrete pulse is not complete digital pulse. Discrete pulse will hold the properties and it holds the segmentations of analog property nature. So that is not a proper conception. That is a misconception most of the you are having. So why we are not connecting the analog pulse directly to ADC means while using a anchulizing filter, that is a band limit filter, we have to smoothen the frequencies. Sorry, we have to limit the unwanted frequencies. Okay, and next with the help of sample and hold circuit, the analog pulse is converted into discrete pulse. Okay, and next that is forwarded to ADC, that is analog to digital conversion. Here the data conversion is going to happen. So this is nothing but this entire cascaded approach is nothing but the concept of converting an analog pulse which is observed from the plant to digital pulse. Digital pulse. Okay, digital pulse. That means here the discrete digital pulse is developed and next that is forwarded to digital signal processor for smooth signal processing. Okay, so what does the discrete signal processor do? Most of you are very familiar with the DSP. So it will convert the digital pulse into a digital binary code or digital binary signal. So this is how the data conversion is done. So here we converted the analog pulse into digital pulse. So in the reverse manner, We can also convert the digital pulse into analog, depending upon the application perspective, depending upon the various parameters involved. The digital pulse is converted again into the analog pulse. The digital binary signal is converted to D to A converter, and next it is forwarded to staircase signal, and next it is forwarded to smoothing filter. So this is the process. This is the process. Similarly, here also we have used a smoothened filter. Okay, and observe very carefully. This smoothing filter is not anchorizing filter. Okay, anchorizing filter is nothing but a band limit filter. So the smoothing filter is nothing but to limit the distortions or harmonics of the staircase signal. Okay. So what is the purpose of annualizing filter or band limit filter? Its purpose is to limit the unwanted frequencies, but the smoothing filter purpose is to eliminate the harmonics and distortions of the staircase signal, where the digital pulse is converted into analog. So how the concept of converting the digital pulse into analog means, so how the process of converting digital pulse into analog means, so from the digital signal processor, the digital binary code is output is observed, and that output is fed as an input to the digital to analog converter. Digital to analog converter. So what does the digital to analog converter do? Digital to analog converter will take the binary signal code and it is converted into analog signal in the form of a staircase signal. In the form of a staircase signal. That means not complete analog signal is processed here. Okay, the digital binary signal is converted into staircase signal, and next that is forwarded to a smoothing filter. So what does the smoothing filter do here? The smoothing filter, what does it do means, the smoothing filter will eliminate the unwanted disturbances and harmonics, and next that is forwarded to, and next that output of analog signal is again forwarded to the plant. So that means this entire approach is nothing but a cascaded approach. Okay, so in this concept of block diagram, we analyzed the analog to digital conversion and digital to analog conversion. Okay, if you still are having any queries, just post them in the chat box. We will discuss at the end of the session. So next we analyzed about the basic concept of digital to analog conversion. So before going into the configurations of a digital to analog conversion, first we have to see what is the process happening. We have, up to now we have the general knowledge about conversion. What is meant by conversion? What is the purpose of conversion and everything? And next we analyze the block diagram of conversion, analog to digital and digital to analog. So first we have to see the techniques involved. What are the techniques involved in these type of digital to analog conversions and analog to digital conversions? After observing and after analyzing this technique, we can see the configurations involved in this digital to analog techniques. So in the previous class, we just discussed about one concept, and today we will discuss only a single concept of configuration, and we will wind this up and we will clarify you most of your queries. So digital to analog conversion, what is happening here? So digital to analog conversion, most in the previous block diagram we have seen, in the concept of digital to analog conversion, what is the input? The input is nothing but binary, digital binary signal. Okay, in some of the literature textbooks, that is called a term called the binary code, digital binary code, or simply they call as a binary code. Why means binary code is nothing but a segmentation of digital perspectives. So in some of the literature textbooks, they will call that as a digital binary signal. Both are same. Both are same. So some people are having the misconception: is binary code and binary digital binary signal same? Is the binary signal and binary code are same or not? Binary code, digital binary signal, and these are all nothing but the synonyms or acronyms. So if we see the basic technique involved, what is the input with respect to the DAC? So what is input here? Input is nothing but digital binary code, which is fed as an input with respect to the digital to analog converter, and we are taking the reference voltage pulse. We have talked. We are clearly stated in the previous class. Whenever the reference pulse is in the concept of the physical quantity voltage, the output we observed is in the same quantity of the reference pulse. Okay, that means here we are using the electrical physical quantities in the concept of this technique conversion. Okay, in the concept of technique conversion, we are using the electrical physical quantities. Mostly we use two physical quantities, that is electrical physical quantities, that is voltage as well as current. Okay, so here in this concept of digital to analog conversion technique, so here we are using an electrical physical quantity voltage as a reference. Okay, the input is nothing but digital binary code. Okay, which is most of you are very familiar. Digital binary code is analyzed with respect to most significant bits and least significant bits. So d1, d2, d3, d4, and least significant bit up to dn minus 1 and dn, and the reference pulse is v suffix r. So after the technique, what actually happens with respect to this concept? So the digital to analog converter, the input is an n-bit binary code, and it is combined with the reference voltage. So in order to give the output with respect to analog voltage. Okay, so the output of digital to analog conversion can be either voltage or current. For voltage output, digital analog converter is analyzed here with respect to the analysis. So that means most of the thing, digital analog converter here, the reference voltage is analyzed with respect to V suffix R. Okay, and the binary word is analyzed with respect to D1, D2, and Dn minus 1 Dn up to Dn. So here the concept of analyzing the digital to analog conversion technique is very very important. So how the conversion is happening here? How the conversion of digital to analog or analog to digital happened here means the concept of conversion with respect to the binary code and reference voltage. The digital pulse is converted into analog pulse. Okay, the output is observed within the form of voltage here V naught. Output is analyzed in the form of voltage here. So here the output voltage is analyzed with respect to constant k. K is nothing but the scaling factor, and V suffix fs is nothing but a full scale output voltage. Okay, and d1 divided by 2 and d2 divided by 2 and d3, this is nothing but the most significant bits, and dn divided by 2 power n is nothing but the least significant bits. So there are various configurations involved in this type of techniques, digital to analog conversion techniques. So the first configuration involved is nothing but weighted resistor type or digital to analog converter, and the second configuration is nothing but r to r ladder type digital to analog converter, and third configuration is nothing but inverter r to r digital ladder type digital to analog converter. So in these three configurations we can clearly analyze the very basic concept we discussed in the DAC, digital to analog conversion. That means the input is nothing but binary signal code, and the reference is nothing but voltage pulse. Output is nothing but the analog pulse observed in the form of an voltage output. Okay, so if we see the first configuration, that is weighted resistor type, we just analyzed the introduction in the previous class. Weighted resistor type, so this is nothing but an operational amplifier IC 741. Most of you are very familiar with the operational amplifier. It is a 5 terminal device. Operational amplifier is having high gain, high precision. Okay, all these parameters. Why? And the with respect to the negative feedback, the overall gain of the operational amplifier is also improved. So this is the nothing but prerequisite knowledge. Most of you are very familiar. So if we see the circuit construction, so the operational amplifier, here we have a negative terminal, that is inverting terminal, and the positive terminal is nothing but non-inverting terminal, and the negative feedback is connected with respect to the negative terminal of the operational amplifier and output terminal of the operational amplifier. So on the summing circuit, so this is nothing but summing resistance. We call this as a summing resistance. A summing resistance is connected to the negative terminal, that is inverting terminal of the operational amplifier. That means if we see this type of circuit schematic, so this look like an inverting mode configuration of operational amplifier. Okay, that means most of you are very familiar. That means if the input supply is connected with respect to the negative terminal of the operational amplifier and the non-inverting terminal, that is positive terminal, is grounded, that is an inverting mode configuration. If the input supply is connected to the positive terminal, that is non-inverting terminal of the operational amplifier, another negative terminal is grounded, that is called as non-inverting type configuration, non-inverting mode configuration. So here what happened, the negative terminal, which is the inverting terminal, is connected with respect to a summing resistance. Summing resistance, that means what we are talking about, this type of digital binary code, that digital binary code is analyzed with respect to the DPST switches here, and those DPST switches are connected with respect to a summing resistance, a summing resistance. So this is about the circuit construction. So if we analyze the circuit operation, so this is a simple circuit using a summing amplifier with respect to binary, with respect to the binary weighted code resistance. So the n number of resistances are connected here. D1, n number of resistance are connected with respect to the switches D1, D2, D3 up to Dn is controlled with respect to binary input board. So these switches are nothing but single pole, single thrown. Most of you are familiar, SPDT switches. This type of switches we have seen in the circuits laboratory and machines laboratory. Single pole double thrown switches. So if the binary input is having a switch 1, so it connected with respect to the reference voltage minus VR, and it is connected with respect to the bit 0. That means whenever the switch is connected with respect to the resistance, we are having the output 1. Whenever the switch is connected with respect to the ground, at that time the output is 0. So this analyzer the operation input of binary code. That means the entire binary code is of type zeros and ones. Whenever the SPDT switch, single pole double thrown switch, is connected with respect to the resistor, at that time the current will pass through the resistor and the input voltage is fed with respect to the the input voltage is fed with respect to the negative terminal, that is inverting terminal of the operational amplifier. At that time, whenever the SPDT switch is tapped with respect to the resistor, at that time the input is 1. Otherwise, if the same SPDT switch is tapped with respect to the ground terminal, at that time the output is 0. So this is very very talkative and important. So focus yourself. So at this condition, so whenever the SPDT switch is connected with respect to the resistance, at that time only the input voltage is fed with respect to the inverting terminal of the operational amplifier. Inverting voltage operational amplifier. Otherwise, if the SPDT switch is tapped with respect to the ground terminal, at that time the input is 0. Input is 0. So if we clearly analyze with this is the operation actually happens. So if we see the mathematical analysis, that means here at this particular terminal, at this particular non-inverting terminal, if we analyze the KCL, what will be the input currents? I naught is equal to I1 plus current flowing in the I1 resistance with respect to the D1 MSB, current flowing with respect to the I2 resistance with the D2 MSB, current flowing with respect to the I3 resistance with the D3 MSB. So this is nothing but the current path. So what is the current division rule in the resistance? I is equal to I1 is nothing but V1 divided by V1 divided by R into D1. So this is nothing but current division rule. So later we just simplified the current division rule and MSBs and LSBs aside. So what will be the output voltage? Output voltage of the non-inverting type, sorry, output voltage of the inverting type operational amplifier is nothing but V naught is equal to I naught into RF. So what is I naught? So this is the term of I naught. So substitute the value of I naught here in the term of output voltage. So if the scaling factor, what we are talking about, so if the scaling factor is 1, resistance of the entire circuit is equal to the feedback resistance, at that time a full scale output is observed when the resistance of the total circuit is equal to the resistance of the feedback circuit. That means Vf suffix s is equal to Vr. That means this is the how we analyze the weighted resistance type circuit. So there are various important points we have to keep in mind in this analysis perspective. So what is the thing here? We converted the digital pulse into analog pulse by using a digital to analog conversion technique. So even the above circuit is operated in the inverting configuration. We can also connect the circuit in a non-inverting type configuration also. So this is what we discussed in the previous class. That means instead of using the negative reference voltage, we can use a positive reference voltage. That is the perspective. That means we connected a negative feedback. We know what is the purpose of negative feedback in this type of inverting type operational amplifier, in order to provide high gain, in order to grab a proper gain value. So if we connect the positive feedback, the output the reference voltage will be positive, and that improves the switching time period of the summing circuit. That means, and second thing is, so this operational amplifier here, this configuration, so it acts like a current to voltage conversion. That's why we use the reference pulse, that is voltage. So, and if we use a 3-bit MSB, and we analyze the entire circuit in a 3-bit MSB, and this that is a 3-bit digital to analog conversion. So that's how the operational amplifier output voltage, sorry, that's how the DAC technique output voltage is analyzed. So this looks like a square wave, staircase waveform. If this output is next passes with respect to smoothing filter, this entire staircases will be eliminated, and the circuit parameters and operating characteristics will be quite linear by after eliminating the harmonics. So there are various drawbacks. Okay, and because of the bit size and the binary code, there are various factors connecting the series of resistances, increase the temperature of the circuit, and with respect to the caliber, using various passive elements and all, that makes the circuit integrated circuit fabrication quite costly and not economical. So our next two concept which we discussed about is R to R ladder circuit digital to analog conversion. So this is a quite different configuration. This is a quite different configuration. So in order to in order to analyze this type of configurations here, what we have to do means, so this is an R to R ladder type digital to analog conversion. So here we use a wide range of resistors. So in order to require the binary weighted resistor type DAC, so this can be avoided by using the R to R ladder circuit type digital analog conversion. So there is a only difference means here where we only used two values of resistances. That means the entire circuit is integrated, and the resistance range is calculated with respect to an equivalent circuit. In the circuit, if we see the circuit, okay, so the entire circuit is operated with respect to two resistances. Okay, so and mostly this is a 3-bit type, but mostly this is a 3-bit type digital to analog conversion. So in this 3-bit type digital to analog conversion, what we will do is the switch position of D1, D2 and D3. The switch position of D1 and D2, D3 are corresponded with respect to an binary word 100. Binary word 100. So and the circuit is simplified and analyzed in the form of an equivalent segmentation. So if we observe this output, if we observe that output voltage with respect to the input, the output voltage V0 is equal to Rf divided by R1 into Vi. So this is nothing but the output voltage of non-inverting type operational amplifier. And next, if we calculate that feedback resistance, what is the value of feedback resistance here? The value of feedback resistance is 2R. Okay, and the value of input resistance is R. And how the input voltage is distributed? The input voltage is distributed among the 4 bits. Even there is a 3 bit DAC. Here we have a reference bit resistor, that is 2R. So that's why the minus 4 are that divided by 4. Why means here we are providing the negative feedback. That's why the reference voltage is provided with respect to negative sign. So after further simplification, so this is the behavior of this is the behavior of the output voltage here. So this is about R to R ladder type DAC. This is a very simple concept. Okay, so what we have done here means a wide range of resistance is required in the binary weighted resistor type digital analog conversion. So this can be avoided by using an R to R ladder. So previously we haven't used this type of R to R ladder. So what is the concept of R to R ladder means? So entire circuit will be converted in the form of an equivalent circuit. Entire these resistances is converted in the form of a ladder. See here. Okay, this resistance is connected in the form of a ladder with an equivalent rating. Okay, equivalent rating. And that what is the purpose of this conversion means, with the help of this conversion we can reduce the behavior of sorry, we can eliminate the number of passive elements count. We can use very less amount of resistance. Okay, that means very minimum amount of resistance is used here. And another important thing is the heat temperature coefficient will be reduced. Okay, and the fabrication of integrated circuit is also easy with the help of this type of ladder type R to R circuit. Only two resistances are required. Okay, and the entire integrated circuit realization is very easy here. So the typical value of resistance is ranged up to 2.5 kilo ohms to 10 kilo ohms. And this looks like a 3-bit DAC. Even though we have an additional grounded resistance, this is a 3-bit DAC. So that means the circuit is simplified in the equivalent position, and the voltage is observed at this particular node. Voltage is observed at this particular node point of view. At this node point of view. So what we analyzed in today's class, we discussed about behavior of. We discussed about the block diagram of conversion. Okay, we analyzed about data conversion, and next we discussed about digital to analog conversion technique, and next we also discussed about the first configuration weighted resistor type, and next we updated the weighted resistor type into ladder type. Ladder type. We updated the weighted resistance type into R to R ladder type digital to analog conversion. Okay.